This video continues looking at prediction with state space models. The previous videos showed how you could form an n-step ahead prediction with the standard state space model, assuming the current state was known. We also showed how prediction can be separated into a part which depends on known information, past, and a part which depends on future or decision variables. This video is going to look at how we can group this information to put it in a more compact form, and it's this compact form we need in order to do simple analysis and ultimately to design our predictive control law. The main thrust we're going to use is to express predictions as vectors of vectors using matrix notation. So the background then. This is what we did in the previous video. We showed that the output predictions could be given basically as a part which is based upon the current and the past measurement. So you can see the part based on xk and dk, and a part based upon the future inputs, which are things that you have to decide. Now you could also do a similar thing for the state predictions if you needed it. Now what we want to do here is introduce the vector of vectors notation. What we're going to do is use a simple arrow notation in order to represent these vectors of vectors. Now the reason we use arrows is because they represent direction in some sense, and so an arrow pointing to the right is going to represent we're moving forwards in time, we're going future. So you'll see here the way we've done this expression, we've said let's write down a vector of future predictions for the state. I've got xk plus 1 at k, xk plus 2 at k, all the way down to xk plus n at k. So I've written the 1-step ahead prediction, the 2-step ahead prediction, all the way down to the n-step ahead prediction, and grouped them all into the same vector. And I'm going to write that as x right arrow k plus 1. So the right arrow tells me this is a vector of vectors. I've got all the predictions starting at k plus 1. Now the nice thing about the arrow notation is it doesn't tell you what n is, so you can be fairly flexible. It can go up to whatever n you like. So the subscript k plus 1 indicates the first value, that's this one here, but actually we don't say what the last value is. We leave that as implicit in the context. And just to re-emphasize here, the arrow pointing to the right means prediction, and that's because when you write, if I write a sentence here, you'll see that going forward in time I move to the right, and that's the simple reason. Now what we're going to do is combine this arrow notation with the predictions in order to do things a bit more compactly. So what you'll notice is if I actually write down what's xk plus 1 at k, there it is, what's xk plus 2 at k, here it is, and so on, I can now get rid of that and just write x right arrow k plus 1, and I get all this stuff over here. Next, what I want to do is separate this into past variables, things that I know, and the decision variables, things that I need to choose, the future inputs. And I can do that like this. I can say, again, you'll see there's my notation, x right arrow k plus 1, and then I've got this vector axk, a squared xk, all the way down to an xk. That's the bit that I know, based upon the current state. And then I have this other bit, which is just based on future inputs. What do we do next then? We want to separate model parameters and data. At the moment they're all mixed together. I've got AXK and ABUK and all sorts of things like that, and I want to separate the model parameters from the input, output and states. So this is relatively straightforward. If you look at this expression here, you can see very quickly how I can separate out the xk. So that's what I'm going to do here. You'll see I can write a matrix a squared all the way down to an multiplying xk. In a similar way, if I look at this vector over here on the right, you'll find that I can take out the variable ukk, uk plus 1k, all the way down to uk plus n minus 1k, and that gives me a vector of future inputs and multiplied by a matrix of model parameters. Now I'm not going to go through that step by step. Hopefully it's obvious to you how this works, but if I do a simple example, let's take this one here. you'll see I've got AB times UK. So there's AB here times the first element in that vector, and then I've got B UK plus 1, so there's the B, and that multiplies on that, and there's nothing multiplying all these other U's, and so we've got zeros across here. So hopefully it's obvious how you construct these matrices, and I'm not going to dwell on that in detail. And the key thing is, you'll find I've now got matrices of model parameters. There they go. And I've got vectors which have got the signals in, the x and the u. So next what I want to do is give myself some names so I can make this more compact. This vector a squared all the way down to an, I'm going to call px. This matrix here, b 0, 0, 0, a, b, b, 0, 0, 0, and so on, I'm going to call hx. And you'll notice that over here on the right, I've got a vector of future inputs, so I can call this u future k. So with the arrow notation. So I put that together, this is what I've got. And the nice thing about this is I've now got a very compact expression that is also neatly separated into things that I know and things that I can choose. You'll see I've got the px times xk, things that I know, and you've got the hx times u future k, and the other nice thing of course is that hx depends solely on model parameters and the u future k is my decision variables. So I've got a very compact notation where I can see exactly what's going on. I can do a similar thing clearly for the output predictions. It's a very similar expression. The only subtle difference here, alright, you've got the bit that depends on the past now includes this disturbance term, which you'll remember is there to cater for not only disturbances but also parameter uncertainty, and I've got a bit which depends on the future inputs. So in summary, we've given a prediction structure which includes the degrees of freedom, which is the decision variables or the future inputs. And so what we can do now we've got this in compact form, is we can say how might I choose my degrees of freedom such the overall prediction is desirable. So there's my predictions. I can either have predictions for the future states or predictions for the future outputs. And the key thing is these are separated into parts which are known. So those bits are known, but then critically you've also got these two parts over here which you can choose. So now it's highly transparent what you can do with these expressions. By the way, there's a little typo there. That should have a subscript x. That should have a subscript x. Sorry about that. But it's now highly transparent what you can do. How do I choose the future values of my inputs in order to get my predictions to do what I want? So you've got transparency in where your flexibility is by using this nice compact notation. So in summary, it's common to use discrete models for prediction, and here we've shown how when you use state space models you can get a compact form, that's the key thing, of the predictions for all the horizons simultaneously. It's been shown that the predictions separate cleanly, and that's really important, into a part which is known and a part which can be selected, and that gives you the flexibility now to say, now it's easy to see how I can use my decision variables. We haven't really given any detailed discussions of how to ensure the predictions are unbiased, which basically means how do you choose this D term, but that will be covered later.